going to be looking at the notes for week 2, April 27th through May 1st. And you don't need to write anything right now. You just need to listen, okay? So the first thing is that we got to think about what we're working towards, actually, is we're trying to work towards this marking period or the rest of the year. We're looking at energy transfer, all right? So we're going to move away from the stuff that we did last marking period in terms of the composition of the atmosphere, and we're working towards energy transfer, how energy moves, both. And as we work throughout this the rest of the year, we're going to be looking at it from a climate standpoint and also from a biology standpoint. Okay, so to kick things off, you don't need to write anything. We just need to think about where the Earth derives most of its energy. All right, and it gets most of its energy from the sun. Okay, now that energy reaches us in the form not as heat. Okay, we don't feel heat from the sun. Okay, for heat to happen, we need matter to touch, and there's just too much space and nothing really there between us and the sun. All right, in that space, there's very few molecules, and they're not touching each other, and we can't feel heat from the sun in that way. Okay, in order to get that heat, we need in order for it to travel this distance from the sun to Earth, okay, almost 860,000 miles from us, all right, we get that energy in the form of light, okay? And when I say light, I mean, which is another way of saying electromagnetic radiation, okay? Electromagnetic radiation is the fancy way of saying light. So it reaches us in the form of light. Now, electromagnetic radiation is a force, okay? And there are 4 forces, just one of which you're probably really familiar with, and 2 of which are way over my head. Okay, so the first force that we're talking about here is gravitational force, right? You experience gravity every day, all right? So it's keeping you stuck to the Earth right now, all right? The other one that we're going to talk about now is electromagnetic force, okay? It's we're going to be talking about light here. The other 2 are really subatomic, all right? They're strong and weak forces. You could get many PhDs within this topic, and I'm not going to pretend like I know much about them. So they're talking about like pieces of atoms, and pieces of the nuclei, and pieces of protons and electrons. All right, we're going to be focusing on this electromagnetic force. Okay, now we are going to be talking mostly about solar energy. So which solar meaning from the sun, which is primarily infrared light, visible light, and ultraviolet light. All right, now that electromagnetic radiation or light travels through space as if it were a wave, okay, and it's traveling at the speed of light, which is pretty darn fast, 186,000-ish miles per second. Okay, now in order to fully understand that electromagnetic light, we need to know a little bit more about waves. Okay, now we're going to be looking at a wave here. So pretend this is a person's hand over here, and they're holding a rope, all right, and it's tied to something, and they're moving their hand back and forth, okay? And we're going to define this term of trough and crest, right? So the crest is kind of the high points between a wave, and the trough is that low point. And the distance between a crest and a crest has this symbol. It's a Greek letter, lowercase lambda, I believe, and it is the symbol for wavelength. All right, wavelength is the distance between 2 crests or 2 troughs in a wave. So crest to crest or trough to trough in a wave. So you're going to need to write this on the note sheet. This is the note sheet that you've got in Google Classroom. All right, you need to be filling in these red terms as we go. Okay, so here's that same image. Crest to crest is a wavelength of light. You can watch this optional video by clicking on the link if you want it explained in a different way, okay? Now, if we think about those waves, all right, the amount of energy that they carry is what we're going to call as inversely proportional to wavelength, meaning a wave with a short wavelength, okay, the distance between the crest to crest is relatively short. That's going to require high energy. So you can imagine this guy over here shaking his arm vigorously in order to make those short wavelengths of light. okay? If a long wavelength, much longer than this one up above, okay, would require this person moving the arm slowly, okay, it requires a low energy or carries low energy. You can watch this video demonstration, and then you can answer these questions on the note sheet, all right, that fall right below this demonstration. Now, we got to think about wave different types of light. All right, so here I've laid out the different types of light that fall within that electromagnetic spectrum. Okay, and there's a lot of information on this chart, so I'm going to kind of walk through it. On the left-hand side, we have things that have low energy, and on the right side, we have things with high energy. Okay, now some of these forms of light I hope you've heard of. We got visible light. We've got UV light that we wear sunscreen, all right, to protect us from. We've got infrared light. We'll talk more about that. Radio and microwaves are also two types of light. And then we've got X-rays. Hopefully you've not had an X-ray, but many of you probably have. And then we've got gamma rays way up here with really high energy. Now, a little bit more about those wavelengths of light. Okay, if we think about radio waves, they carry energy with them, but very little. Okay, they don't really interact to a great degree with molecules. Microwaves cause molecules to rotate, okay, which is why your microwave works the way it does. It causes the specifically water molecules in the food that you throw in their microwave. It shoots microwaves at them, causing those molecules to vibrate a lot, or sorry, rotate a lot. And when they rotate, they heat up the food because there's more molecular motion, causing your food to be warm, okay? Infrared light, okay, when infrared light interacts with a molecule, it causes the molecule to vibrate, okay? And that vibration is, the more it vibrates, the more it moves, the greater it feels in warmth, okay? We've got visible light. When a visible light interacts with a molecule, it causes the electron to move from one orbital to the next, okay? And when that does that, it releases a little photon of light that we perceive as color, all right? Depending on kind of where they jump and how many are jumping, we perceive different wavelengths, or we perceive different colors. Okay, and we got UV light way up here that causes molecules to break apart. They break those chemical bonds. We've got an O2 molecule getting hit with UV light, causes those molecules to split apart. All right, this is why UV light is a problem when we're exposed to it in high quantities. All right, the more that UV light interacts with our skin and the cells within it, the more things that can break apart. And when you have the longer you are exposed to that, the greater your chances of getting things like skin cancer. X-ray converts atoms and molecules into ions, and gamma rays have enough energy to basically like break apart atoms into their pieces. It just kind of it just sort of breaks everything, obliterates things into pieces. All right, now if we think, we're going to be spending most of our time talking about electromagnetic radiation, and we kind of have broken those into different classifications of light. We get kind of two categories: things that are produced by the sun and things that are produced by other astronomical events, okay? And each type of electromagnetic radiation has a different amount of energy, different wavelength. We just talked about that. You've got a very similar chart right down here, okay? Got those different wavelengths of light. And due to this variation in energy, forms of electromagnetic radiation will interact with the atmosphere and Earth in different ways, okay? We have also figured out how to create some of these types of light, which is why we can like use X-rays to see your bones, okay? We can manipulate radio waves to produce, to transmit radio signals, right? Microwaves for food, etc. Okay. Now, the infrared, visible, and UV light, those things, most of that light comes to us from the sun. These ones at the high end of the spectrum, other astronomical processes in space, as well as radio waves and microwaves. So we just split that into categories. All right, so the stuff that's coming to us from the sun, infrared, visible, and UV. And then we have these other categories from other astronomical processes. Now I've labeled here kind of the stuff from the sun. You don't need to add that to your sheet. But this diagram down here just kind of shows you kind of which types of light are making their way to Earth's surface, okay? You've got the visible spectrum of light. Almost all of that's making its way to Earth's surface. Most of the infrared is making its way down, but not all of it, okay? Or actually not most of it. Some of it is making its way down, all right? And just some of the UV light is coming down. We get some radio waves, all right, and are making their way to Earth's surface, but not really any gamma or X-rays. I'm going to talk about that more in a minute. So let's kind of break those down into their individual parts, okay? So I've got different types of electromagnetic radiation. The first one, let's look at radio. So the long wavelengths of radio are absorbed in the upper atmosphere, and the short wavelengths of radio waves can reach Earth's surface. This is true for microwaves as well, okay? The shorter ones are absorbed by the upper atmosphere, and the longer ones can reach Earth's surface. Actually, opposite, sorry. Infrared, all right, now this one is the key one, so make sure you capture all of this. Infrared is absorbed by greenhouse gases, like CO2, CH4 is methane, and H2O, water, is actually a greenhouse gas. So infrared is absorbed by greenhouse gases in the atmosphere. And these wavelengths of light can then be re-emitted by the gases and scattered throughout the atmosphere. Okay, they go kind of shoot in all directions. And I'm going to show you a couple of images of that. Visible light reaches Earth's surface. Okay. UV light, most of that UV electromagnetic spectrum is absorbed by the ozone layer in the Earth's stratosphere. All right, but a small amount of that UVA radiation reaches Earth's surface, which is why you need to wear sunscreen on a really sunny day. Gamma rays and X-rays are absorbed by Earth's upper atmosphere. Okay, you can watch this video to hear someone else explain that. But I would like you to take some time to kind of look through this diagram and make sure you read each of these boxes and kind of try to interpret this diagram. These little squares are kind of meant to be windows or screens as things are passed through, or for infrared here, right, we've got these wavelengths of light coming in and they're kind of being absorbed and re-emitted, and they're kind of shooting off in all directions. So towards the end of this sheet and the end of this video, what I'm going to need you to do is, we're not going to ask you to do all of them. We're just going to ask you to look at gamma ray, visible, and infrared light. And I need you to label these 3 red boxes with the types that they are. All right, this dot arrow over here will come into the analysis questions. All right, so you need to label these red boxes, and then you need to answer the analysis questions.